Assalamualaikum and good day. So today we move on to the next section, still in chapter 6 on simple solutions for laminar, viscous, incompressible fluids and Navier situation. Okay, so here is the learning outcomes. Right, so we'll focus on need to simplify the Navier-Stokes equation to solve fluid problems. Analyze and simplify NSC in laminar flow between two fixed parallel plate. Analyze and simplify NSC in fluid flow. Okay, so we look at all these things. Okay, but before that, we'll review back on what we learned from previous week. Okay, so we go back to your previous week notes. Okay. So previous week we've been introduced to these two equations. So one of them is a continuity equation. So this is very important. So that's what just want to review back on this. So yeah, we have gone through the derivation, but we'll look into just focus on the end of the continuity equation. So if its case was steady flow, where there's no change with respect to time, so the continuity equation will become like this. Just these three terms equal to 0. And if it's incompressible flow, so it's steady flow and incompressible flow where density is constant, then this will be equal to 0. Just partial u over partial x plus partial v over partial y plus partial w over partial z equal to 0. So this is a final continuity equation for case of steady flow and incompressible flow. Okay, so it's very an important equation. If you look at this equation, it tells you the u is the velocity, right? So it's velocity u, velocity in the x direction, v velocity in the y direction, w velocity in the z direction. So it means that the change of the velocity in its dimension, in its directional dimension, all equal to 0. Now we shall take a look at the Navier-Stokes equation, so which we have gone through last week. So this is what we have. So this is the end product of the Navier-Stokes equation. So this is only for the x direction, right? So you have this partial over t, and this is the term. So the velocity terms, the change of velocity in terms here. The pressure gradient, gravity force, and here are the terms from as a result of the shear stress and normal stress. Okay, so today we'll shall take a look how we can, because we know this is the equations, right? But we don't know what is the use for. I mean, it's just an equation tells you about the velocity, right? And then you have term from the pressure gradient, gravity force, and here's the normal shear stress terms, but it doesn't help us in anything. So today we'll look at how we can especially derive the velocity and velocity profile or the equation that tells you how you can obtain an expression of the velocity. In the case for the x-axis, how we can obtain the u as some function of some variables. And today we'll look into that. So we'll go back to our notes today. All right. So why we desire simple solutions to NSE? So we call that. I mean, so from this we know for Navier-Stokes equation in x directions, the case for the general equation for Navier-Stokes equation is given this, right? So the change of the velocity in terms of time, and here are the terms that tells you the change of the velocity if direction x, change of velocity direction y, change of velocity direction z, pressure gradient, the gravity force, and here are the term from the normal shear stress and the normal stress, right? This for x direction, and this for the y direction, and this also for the z direction. You can see that yeah, if y direction, the velocity component will be v. For the z direction, the velocity component will be w. So the velocity is according to the direction. And also you see, yeah, vw. Okay, so this is the final form of the Navier-Stokes equation. All right, so we're going to look at these terms here. These terms here in mathematics, this is non-linear, right? So non-linear because you have this variable here u, and then you have the gradient term here. It's non-linear, and these terms here we call convective acceleration terms, right? So remember in mathematics, if this is actually a linear differential. Sorry, it's not linear. It's non-linear. It's a differential equation, right? And to solve a differential equation, you need to integrate it. And solving linear equations means that you want to solve the variable here, which is here its derivative square here. Means that solving here, you want to find the expression of mu. Right? So solving differential equation means that you want to find the expression of u, of a some function of a variable. So roughly according to either x, y, or z. So either that. So this and this knowing the expression of u is what we want. I mean, means that you know the data between your control volume. So this what is our objective of having this Navier-Stokes equation is to find is the expression of u, and once you got the expression of u, you can get the value for the velocity u. Okay. Okay, so let's so this is convective acceleration. So and if you look at if you can get rid of this term here, that is non-linear. And remember in mathematics it has no analytical solution to solve a non-linear expression term. So you need to get rid of this term in order to solve this differential equation. Okay, and yeah, there are some conditions in order to get rid of this convective acceleration term. So today we look into that. Right, so refer to the NSE or Navier-Stokes equation, nonlinearity arises due to the presence of convective acceleration terms. Right, so get back, so convective acceleration terms because of this variable u, and then you have partial u, variable v, partial u v here. So it's really difficult to solve this analytically. Can we solve this numerically? So that which is bound to some error. Right, so no general analytical scheme to solve nonlinear partial differential equation. So like I said, however, there are some conditions that we can solve convective where these convective acceleration terms can be zero. So in this case, the exact solutions are possible. So in this special case, have condition here, which one, the steady state, to the laminar flow. right? So I think you know what steady state is, right? Steady state is when the case when all the values remain the same at that particular time. So for example, is t equal to 0, that value u, let's say, for example, u will always remain to 3 meters per second. And if t also equal to some time, in 10 seconds, u will also remain to 3 meters per second. So it means that here now is a steady state. And so on. If t equal to some infinity also, u will remain the same. It's 3 meters per second. This is what we call a steady state. Also, laminar flow, I think, yeah, by now you should know what's a laminar flow. We have turbulence flow, we have transition flow. So laminar flow is relatively small range of velocities. Okay, so we take a look at this case one, steady laminar flow between fixed parallel plates. Navier-Stokes equation. Okay. So this is a case in a steady state, with the value remain the change between any time, and then laminar flow means that the velocity is relatively low, right? Not that the the flow is uniform, so it's laminar flow between. Now we just focus on the flow between fixed parallel plates. So this means that this fluid flow flows within these two fixed parallel plates, and it's a two-dimensional. I mean, even though we analyze it in the two-dimensional, even though we know we have x, y, right? X is along the axis, y is the height, z is the direction coming out of this line, right? So this Navier-Stokes on the x direction. So it's like a pipe. It's like a cross section of a pipe, right? So this is, and now as we look at the case one between fixed parallel plates. So we are interested in knowing this expression of u, right? Expression of the velocity u. So you know u is the velocity along the x direction. So, and I think you know it from your fluid mechanics one, the velocity profile for a flow inside a conduit, right? Cross section will look something like this: a parabolic profile, where the maximum velocity in the middle, and then the velocity will be equal to 0 at the boundary, right? It's like a pipe here. So here is a case for a steady. The u remain the same within in any time, and then a laminar flow. I mean, the flow is uniform, it's not in transition, or it's not turbulence, relatively low velocity. So we shall take a look like how we can apply the this Navier-Stokes equation, right? And then we can somehow produce expression of velocity u here from this Navier-Stokes equation, this long Navier-Stokes equation. How can we produce this expression of u from again? Okay, so here's the Navier-Stokes equation. Now we're going to apply, because you know the boundary condition on within this control volume. We can apply, we can, and this condition of steady and condition of laminar. So we can apply that to simplify this Navier-Stokes equation, and we can, in the end, somehow we can solve the expression of u, or expression of the velocity, which is what we want. We want to find some expression of the velocity u, right? In this case, as some u, expression of u as a function of x, right? So because u is the velocity in the direction of x. Oh, sorry, my mistake. So u as a function of y, right? So that's here in this case, u changes with respect to y. Is from u equal to 0, and it changes to some values, and then you hit the maximum velocity in the middle point. So that's why we want to find what is the expression of u in terms of some function of y. Okay, so we shall do it together, right? So we're going to simplify this equation, and then in the end, we're going to find this u is a function of y. Okay, so we shall take a look first. Here is a steady state, right? Steady state, so means that all the variable with the function, it relates to the time is equal to 0. So it's steady state, so you know that du per dt here equal to 0. And here you can take a look as there's no velocity in the y direction, right? So there's no y direction. There's no the velocity in x directions is u, velocity in the y direction is v, and velocity in z direction, which is coming out of the slide, is z. Right, just the common symbol for the velocities. Oh, sorry, this is w. W. Okay. All right, so no velocity in the y directions. That's why v equals 0. Here v equals 0, distance is 0. And then also no velocity in z direction coming out of the slide. So w is equal to 0 as well. So this will become 0. So now we have simplified this Navier equation to this. And also this term here equal to 0. Yeah. Right. Right. So this term here become 0. So this due to the fact that, from quantity equation, remember we just review the quantity equation just now. So du per dx plus dv per dy plus dw over dz equal to 0. So as v equals 0 and w equals 0, right? So you know that v equals 0, w equals 0, dv per dy is 0, this w per dz is 0. So from expression, this 0, 0, so equal to 0, so du per dx must be 0 as well. So that's why this term is 0 as well. But by counting the equation, and you know that from this case, v equals 0, w equals 0, this term is 0, 0, so du per dx equals 0 as well. So now we have all these the terms on the left side here. It's all equal to 0. So it's easy for us because we've get rid of this non-linear terms, and we've get rid of this variable type of the time. So this becomes 0, and from here on this side we can solve it, right? And then also you know that this direction u does not change with respect to this y direction. U does not change with respect to z direction. So we can. So first we we know that the gravity. There's no gravity on the x direction, only gravity on the y direction. So this term is equal to 0 as well. So now we have make it more simplified. Right, and u does not vary with respect to the x-axis, right? Right, so u does not vary with respect to x-axis because u only varies with respect to y direction only. Right, so in terms of x direction, it does not change. So this becomes 0. And in terms of z direction also, u does not vary with z also. So u put this as u put z is equal to 0. Right, z is the direction coming out of the slide. So we just left off with these two terms here: negative partial p of x plus partial square partial u per partial y square equal to 0. So it's easy for us. Like looks like. Okay, and now we apply to the y direction as well. So for y direction, Navier applying to the y direction. So these are the equation in y direction. Partial v or partial t plus u partial v or partial x, so on. So again, we apply the condition steady state, change of the time equals 0, the convective acceleration equal all equals 0 because there's no velocity, there's no v does not exist. This does not exist, right? No velocity in the y direction, so all terms become 0. And you know this term 0 because the new v does not exist, right? Only u. So we just left off with these two terms here. Now we apply to Navier's expression in the z direction. So steady state equal to 0. No velocity in z direction, w equals 0. No gravity force on z direction. And no velocity in z direction, right? W equals 0. So we just left off with partial p or partial z equals 0. So it means that there's no in z direction, there's no value. Right? We don't have to worry about this z direction there. So now we have simplified all the lengthy Navier equation into just this three equation, a simplified equation here. And our objective, remember, is to find the expression of u, right? And if you look at this equation here, so particularly on the first equation here, this is a linear differential equation where you can solve for the u here, right? So because this can bring it to this side, and then you can just integrate it with respect to y, and you can solve for the u. So that's our the objective here, to find the expression of u, and we can use integration to solve this because it's a linear differential equation, so we can solve it. So we rearrange here, right? So partial u partial y square equal to putting this side and the viscosity on below here, right? So this, I think by now you can see this familiar form, right? So now you can apply the integration, partial y equal to 1 over viscosity partial p over partial x, right? We have a constant C1 here. Right, so and now you have a partial u partial y and can integrate again. And now you can have the general form of the expression of u. U equal to 1 over 2 viscosity partial p over partial x, y squared plus C1y plus C2. Right. Okay, so this is not a finish. I mean, our business is not finished yet, so because we have to solve for this constant 1 and constant 2 here. And here is just mathematics, right? So remember that if you know the boundary condition, initial condition, or boundary condition, or at y equals 0 or at u equals 0, and solve for C1 over C2 here. So according to your case study here. So now we're going to do that. We're going to solve for the u, and you solve for C1 and C2. So first we look at the convention, the origin, right? The coordinate here for this laminar flow between fixed parallel plates, right? So here the origin will be here in the center line of the fixed parallel plates. So center line, right? So x. So x's origin will be at there. So we apply the boundary condition. So you know at the parallel plate, if they're at the upper part or the lower part, the velocity that touch the plate will equal to 0. So you know we can apply the condition. So then at y equal to h, it's at the upper plate, u equals 0. You put into the equation here, right? At y equal to h, u equals 0, and solve for C2. So we have this expression here, C1 1h plus C2. And then you apply another boundary condition, which at the lower plate, it's at y equal to negative h. So u at and that y equal negative h u equals 0. So you apply that. All right. So you have here is the two equations with two variable, and we can solve it. And we can solve the variable here for C1 and C2. All right, so you can solve that by adding equation 1 and 2 and solve for C2. So you have C2 equal to negative 1 over 2 viscosity partial P over x and h squared. So that's the value for C2. So you can put C2 back into the equation 1. Put the C2 back in equation 1 and solve for C1. And you found out that C1 is actually equal to 0. So this is the velocity profile, right? So remember, we want to find the expression of u or call it velocity profile. So u equal to 1 over 2 viscosity partial P over x y squared minus h squared. So that's the velocity profile. Okay, so from this velocity profile, so we can know the velocity at any point inside your control volume here, right? So if you want to know, for example, you want to know what's your maximum velocity, which is at the y equal to 0, right? So you can just put y equal to 0, and you can solve for the velocity profile. So that's yeah, so it means you're solving the velocity profile using the Navier-Stokes equation. Okay, so there are other parameters that we can use once you know the velocity profile that normally is being asked in the fluid mechanics too. One of them is the volume flow rate, or Q equal to volume flow rate. So I think you know what's the volume flow rate, right? So I think from your fluid mechanics one, so okay, so it's Q. So volume flow rate equal to the volume times the cross-section area, right? Cross-section area that is facing the flow. All right. So in this case, because it's a two-dimensional, no Z, so volume flow rate will just equal to some velocity times the dimension h. So just this height here. So that's normally the cross-section area will be this height times the length that is coming out from this line. But because it's two-dimensional, so you just times 2h. So mostly the volume flow rate is velocity times, yeah, just this dimension here, 2h. That will be our volume flow rate. So in this case, also the volume flow rate can be solved by this integration here. Volume flow rate is integration of the u, expression of u, for integrate over the length, which is from the lower limit negative h and the upper limit h. So this is actually this same thing as here. The volume rate is equal to the expression of the velocity, and from the lower limit and the dimension, the lower limit and the upper limit h. Okay. Like the same thing, it means we become a 2h from the integration. Okay, and so we know that the general form, so this is the general form of the volume flow rates is equal to the lower limit and upper integration of lower limit and upper limit of the expression of velocity over respect to the y, or the direction of the height here, right? So it's the general form of the volume flow rate. So you know our velocity profile here, u equal to this expression. So we can substitute that into here. All right, so now we have this expression here for the volume flow rate. Q integration of H minus H 1 over 2 viscosity partial P over X y squared minus H squared y. Right, so now we can integrate, can use the integration, right? So I think you know how to solve integration, and we have this volume expression for the volume flow rate, which is this one. So this for the volume flow rate expression for the case of steady laminar flow between fixed parallel plates. Right. And if you know the delta P, the pressure drop between some distance here, you can relate that to the partial P over partial X. This is the normally with a measurement with flow measurements, you know, normally you know the pressure drop between distance at some distance L, so you can use that the data from your measurement from your pressure transducer pressure drop delta P over the distance of that pressure drop equal to the partial P or partial X negative. Right? Negative because you know the pressure drop will decrease along the X direction. So hence, you know, this can lead to the delta P over the L. You can put it into the general equation for the volume flow rate, and you have this expression for the volume flow rate. Also, this is another parameter that we can use after you know the velocity profile, which is the mean velocity is equal to the volume flow rate divided by 2h. So the and that from here q divided by 2h. So we have that mean velocity h squared plus L over 3 viscosity. And also the maximum velocity, right? So the maximum velocity is located at the y equals 0. So just use the u max, the velocity profile, and you just apply y equals 0. So you have that here is square for 2 viscosity plus P of x. Then you have it, which is, can relate to the mean velocity. Mean velocity is given this expression. So you can simplify the u max just equal to 3 over 2 the mean velocity. Right, so that's the mean velocity equal to this expression. Okay. All right, so that's the case 1, steady laminar flow between fixed parallel plates. Okay, now we go on to the case 2, which is co-ed flow. Right, co-ed flow is still we have a plates. It's a flow move between 2 plates. One is a fixed plate, but the other one is a moving plate. Remember, in case 1 we have a flow flows between 2 fixed plates, but now we have one is fixed plates, and the other one is a moving plate. And also now, due to this physical nature, the origin now mostly we put the origin now on the fixed plate, right? And then normally the height we denote that as b. So the velocity is applied, constant velocity applied at the moving plane. So this we call it a co-ed flow. Flow between 2 parallel plates, but one moves and one is fixed. Right, and it's still a steady and incompressible flow. Means it's always still incompressible flow. Density does not change. A case where so co-ed flow is a case where one plate is fixed and one plate moves with a constant velocity. So normally we designate the origin y equals 0 on the fixed plate, and we designate the distance between plate as b. Okay, so now we shall take a look like how we can use the Navier's equation to find the expression of the, again, we're going to find the expression of the velocity u, right? Which is the velocity profile for this particular condition, which is quiet flow. So one fixed plate and one is moved. So you can imagine that the velocity and the profile for this is the u equal to 0 at the fixed plate, because you know the fluid is a no slip condition, where the velocity of the fluid particle will equal 0 at touching the fixed plate, but it will increase until it will the velocity that touch the moving plate, that velocity will equal to the velocity of the moving plate. So imagine the velocity will increase from 0 until in the end become the same as the velocity of the moving plate. So we're going to find that. We're going to find this expression of or can see the formula for u with respect of some function of y. So again, it's still a steady state, and it's a laminar. Okay, so we apply this Navier state to this condition. A steady state, where it is the term here, it come to steady state. Also, change of variable in terms of time equals 0, right? And then there's no velocity in y direction, right? Because you know it's presently on u, v equals 0, w equals 0, right? So you want to simplify this Navier equation. And as you know here, from the continuous equation, du per dx plus dv per dy plus dw z equals 0. So as v equals 0 and w equals 0, v0, w0, so this term will equal to 0 as well. That's why you have all this left term here become 0. And you know that there's no gravity force on the x direction, right? So this becomes 0 as well. And velocity does not vary with x, so partially u, this term becomes 0. Also here, yeah, z is direction coming out of the slide, becomes 0 as well. So we just left off with just two terms here and equals 0. So we shall take a look at that. So we are just left off with two terms equal to 0. And remember, when to solve for the velocity profile u equal to fy, right? So it means that, yeah, now it becomes linear. So you can just rearrange this and solve for the u. So you can integrate this twice and then you can solve for u. So that is our strategy here. Right. So now, yeah, we rearrange, then we integrate that. Right. So you can see, yeah, the flow, the methodology is the same as the case one, two parallel fixed plate. Then by second integration here, you can have yeah, the expression here, u equal to 1/2 viscosity partial p of x y squared plus c1y plus c2 here. All right, so we want to solve for the c1 and c2, so we apply the boundary condition. So apply boundary condition at y equal to 0 and at y equal to b. So at y equal to 0, velocity equal to 0. At y equal to b, velocity equal to u. So I leave you to that. I mean to solve it for C1 and C2. I think you know it. You have learned that from your calculus, how to solve the two constants with a two expression, known expression based on the boundary condition. So yeah, so this is the final general form of the velocity profile used for quick flow. U equal to the constant velocity of the moving plate y, variable y over the b is the distance, plus 1/2 viscosity partial p partial x times the y squared minus by. And yeah, if you want to put it as a dimensionless form, so dimensional form is that we just make a ratio of our expression here. So we make ratio of our variable u here in terms of the velocity of the moving plate. So if you divide by the capital U, so we have an expression become this part here. And also if you want to just take a look at the here, we can take out or we can express this term here, v squared over t over 2 viscosity capital U partial b of x here. That's of some form of p. We express it in terms of p. We can and we can take a look at the effect of what if we change the variable p here. See what is the effect of the velocity profile. Right, so this what happened here. If you change this value of p here, you like a plot the velocity function u. Right, we have a fixed plate and a moving plate. Here, if p equals 0, it's become linear. Right, so p equals 0 means distance equals 0. You just left off with a y over b. You have a linear velocity profile. So if you p equal to 1, so you have for forward the curve is move forward, and if you 2, the curve will become more forward direction, then 3 will become more forward, and then if -1 it become a bit towards to the back. The more the value of p, more the negative value, the more it will be the curve towards to the back. So here, yeah, once you know the velocity function, you can just play around. Right here, we can just play around with the parameter here, the parameter of constant p of some value of constant p here. So you can change your velocity profile. Let's obtain velocity profile. Okay. Now let's take a look at this velocity profile u from Fy. The simplest type of quick flow is pressure gradient dp of dx equals 0, and the velocity function become u over the capital U over y over b. So velocity u varies with linear with y. Moving plate and slip plate. Okay, so now we'll take a look at some problem here. Example of fluid flow problem. So here we have a wide moving belt passes through a container of viscous liquid. So here you have a belt moves in vertical direction and passes through a container of viscous liquid. And here's the liquid here. The belt moves vertically upward with a constant velocity v naught, as illustrated in the figure. The v naught goes up. So you have a thin film that follows through this the belt here. Right. So here is the case that the figures show here that the thin film developed. It's like the thin film developed with a thickness of h, right? So fluid thickness of h here. And again, this is a steady state. Even though, yeah, I mean, in reality, if you go up, the thin film will fall down, but here is in steady state, so everything is steady here. So it's like the belt moves up, and but we analyze this in a steady state. So in the steady state, you have a constant fluid thickness h. Throughout here, you have a constant thickness of h, and also, yeah, so there'll be gravity effect on this fluid here. Because of viscous of forces, the belt picks up film of the thickness h. Gravity tends to make the fluid drain down the belt. So assume the flow is laminar, it's steady and fully developed. So question, so use the Navier-Stokes equation to find expression for average velocity v of the fluid film as it drag up the belt. So we are asked to find the average velocity. What's the average of velocity of the fluid film here as it square cup right out to the back. We'll find the velocity of the fluid. And we have to use the Navier equation to find the average velocity. So we look back, what is the formula for the average velocity? Right, so average velocity or the mean velocity, right, is the Q divided by the 2H, or the volume flow rate divided by this dimension, the total length of the flow, 2H. So we have to use that expression to solve the problem. But here, our problem here is in the case 2, which is the co-ed flow. So the strategy to solve this, right, to find the average velocity V of the fluid film, so it's two-dimensional, so average velocity can relate to the volume flow rate per unit width. So velocity equal to the volume flow rate per unit width, right? So here is total width is H, right? Total width is H. So the mean velocity will be just V equal to the volume flow rate divided by the H. And to find this mean velocity, we need to find the volume flow rate first. And to find the volume flow rate first, we need to find the velocity profile, or the velocity distribution, which is to find what is the expression of V, the velocity in the y direction in terms of some function of x. As you know, the volume flow rate is equal to the integration of the upper limit. Here we have the upper limit is from 0, and the lower limit is 0, and the upper limit is h. So integration of from 0 to h of the velocity profile v with respect to dx. So means that we have to find the what is the expression of velocity plus v. So as you know, velocity v is the velocity in the y direction. So we have to find we have to use the Navier equation in y direction. Right, so the flow is fully developed. So you know that the u equal to w equal to 0. So from quantity equation, we have dv per dy equal to 0, and for steady state, dv per dt equal to 0. And so the velocity profile is a function of velocity to go to some function of x. So the NSC, so Navier equation is, so just look at the x and y and x and z direction. That's all equals 0. Right, so we just I think by now you should know that y now it becomes 0, depends on the direction. So now we have the partial p over x is 0. So partial p over z here equals 0. Right, so now we're going to find the expression of velocity in y direction. So you apply the NSC in y direction. Right, so this is the channel equation for the NSC in y direction. Again, we apply the condition. This steady state 0. This converticism is 0 because of direction. Partial the gradient is not. So here, the pressure along the y direction is equal to 0 as well, because the partial p over partial x here equals 0. Change of pressure on x is 0, and also at the film here, x equal to h here. I mean, x equal to h, x equal to 0 here. This atmospheric pressure, so means that pressure is constant on this type here, on this line here, right? Line here, pressure is constant because here the pressure is on the for surface here is open air, so pressure here must be atmospheric pressure. And as you know, partial p or partial x also equal to 0. There's no change in the x direction, so means that the pressure inside this fluid here is also equal to atmospheric pressure here. Hence, partial p or partial y here must be equal to 0 as well. So no velocity in change in y direction here, right? Because velocity will change with respect to x here, right? And no velocity change in the z direction here. So that's why it becomes 0. So we just left off with just two terms here. And this is right. So this familiar to you, linear differential equation. We can solve this, right? So we arrange that in terms of here and solve for. So here, we can change to that to a specific way, right? So we can integrate that. Right, first integrations, you have the C1. Right, so now in this case, for wet flow. Okay, so if you asking like why, so this is a fixed plate here, even though it's an open air here, but it is actually a fixed plate, so that's why it's still a wet flow. And this plate here moves, and on the low part here, the fluid does not move. Right, it does not move because it's at steady state. At this particular instant of this steady state, it does not move, and this actually resembles a fixed plate as well. So that's why this is an example of wet flow. Okay, so solving for C1, apply boundary condition at x to h, and so all right. So now we want to apply the boundary condition, and to apply the boundary condition, we have to look at the lower limit and the upper limit. So at the upper limit here, which at the x equal to h, right? It's open to the atmosphere, so it's an open surface. So we can use this condition here. So I think you should remember this condition here in your fluid mechanics 1 on surface tension, right? So tension for of a steady state. Here, the shear stress is equal to 0, right? So at the here, if now it's a fixed plate, so the shear stress at this at the x equal to h here is equal to 0. So if you remember from our previous week, the shear stress formula, shear stress xy equal to the viscosity times the gradient partial u partial y plus partial v partial x, right? Equal to, yeah, right. And we know that there's no velocity u involved here, so this term will be 0. So just left off this term. The shear stress equal to the viscosity times partial v partial x equal to 0. So we can use this boundary condition here to apply to this formula. Right, so this equals 0, and put it into this equation, this will become 0. And then, this is at the x equal to h. Can solve for C1. So that's what we're doing here. So hence we obtain the equal to 0 and sub into equation 5. And then at x equal to h, so we have the C1 equal to negative the specific weight here divided by viscosity times h. So we solve for C1. So once we know C1, now we're going to solve for C2. So C2, we integrate this further, right? We're going to put the C1 into this equation. Now we have for second integration, we have v equal to this expression here, and we're going to solve for C2. So solving for C2, we have to apply another boundary condition. So we look at the x equal to 0. So x equal to 0, the v will equal to v naught here. So solving for C2, we apply boundary condition at x equal to 0 or v equal to v naught. So you have to C2 here equal to v naught. So hence the velocity profile distribution will profile, the general form will be v equal to this special weight over the 2 viscosity times x squared minus the special weight h over the viscosity x plus v naught. Okay, so now we have found the velocity profile, but we have not done yet because our objective is to find the mean velocity, right? Mean velocity. So we have found the velocity profile, but we need to find the mean velocity, and to find the mean velocity, we have to find the volume flow rate first. So volume flow rate can be calculated by this expression here, which is integration of the lower limit, upper limit, the velocity expression dx equals, and we can solve that. So we know the expression for v, so you just substitute the expression for v into this. So we have here this here, integrate over the lower limit and upper limit, and yeah, so we have to solve this integration. So we have that the after it be integrated, so you have the q equal to v naught h minus h3 over 3 viscosity. So this is what we want to find. We want to find the average film velocity v, where from the general equation, which is the volume flow rate equal to the velocity times h. Sorry, the velocity will equal to the volume flow rate divided by h, right? So q divided by h here. So you have that the average film velocity given by this. So v equal to v naught minus the specific weight times h squared over 3 viscosity. Okay, so I think that's all for today, right? So this so we have solved the Navier equation. First, we simplify it, and then we solve for the velocity expression, where we look at the problem case by case. Depending on the case problem, we put in the boundary condition, and then we solve for the velocity profile, or the velocity distribution, or the formula for the velocity. And once you've got the formula for velocity, you can use that to find other parameters such as the mean velocity or the volume flow rate. Okay, so with that, I end this class. All right, so thank you very much.